going to be about error resilience in an interactive system. You have two parties that are communicating over a channel, and the channel has some errors in it. The error resilience of the system will be, I'll define it formally, but the high level is that it's the maximum fraction of errors that the system can tolerate. We want this to be higher and higher. And the whole point of this talk is to show how one idea, which is the idea of feedback, improves the error resilience in multiple different settings of interest. So let's start by defining the error resilience. Here is a two-party setting. There are two parties, Alice and Bob. These are probably your friends if you've been to many communication complexity talks. Alice has a message M that she wants to send to Bob. And the trouble is that, like I said, the channel has errors. So there's an adversary sitting on the channel. The adversary sees Alice's message M. He sees all the communication that happens over the channel. And he can corrupt a constant fraction of the symbols that are sent over the channel. So if Alice were to send M directly, Bob will not receive M. He will receive a different message, M tilde, that is different from M in the constant fraction of the locations. But we want Bob to recover M exactly. And the way to do it in the presence of an adversary is to use error-correct encodes. Now, instead of sending M directly, what Alice does is she takes an error-correct encode C. She encodes M using C, and she sends the encoding over the channel. The adversary will still corrupt some fraction of the symbols over the channel as before, but the property that an error-correct encode gives us is that as long as this fraction is small enough, Bob receives a different C tilde that still has enough information so that Bob can recover M exactly. So it will be corrupted. Bob will receive something different, but he can error correct and he can get M exactly. So how small is small enough? Well, this fraction of errors that you can tolerate is what is called the error resilience of the one-way channel, because there's only one message being sent. And it is known that this value is 1/2. If the fraction of errors is less than 1/2, then there is an error correcting code that Alice can use to send M over the channel. But as soon as the fraction of errors becomes more than 1/2, when the adversary can corrupt a majority of the symbols that are sent, then there is nothing Alice can do to send M over the channel. So it's a matching upper and a lower bound, and we know this number is exactly 1/2. Okay, so let's generalize this. And the generalization is to consider a setting where more than one messages are sent back and forth. So earlier we had only one message from Alice to Bob. Now we have a protocol that has many messages that are exchanged back and forth. So here Alice sends the first message. Then Bob will use this message to compute his second message, and he will send that to Alice. Then Alice will use this one to compute the third message, and so on and so forth. The protocol will go on until eventually they compute some function that they wanted to compute. Okay, so again, there is an adversary on the channel, and the adversary can corrupt a constant fraction of the messages. And we want the protocol to work despite these corruptions. So this problem is entirely different. It actually has many new challenges. For example, one challenge is that because the messages all depend on each other, if you corrupt one of the messages, then somehow all the future corruption is also affected. If Bob does not know the first message directly, then he will send something incorrect in the second message. And you need to take care of this. You need to correct errors as they happen. You cannot wait too long. But I will not focus on many of these challenges. I will simplify the setting greatly, and I will only consider the simplest possible interactive setting, which is the setting of message exchange.
Sorry, Raghuvansh, could I ask a question?
Yes, yes.
Hi, it's Yanai. So when you say that the adversary could corrupt a certain percentage, do you mean out of each message separately, or because if they corrupt the first message, for example, it means that they assume that there are going to be at most so and so messages if they can only corrupt a small percentage. So what's going on there?
So that's a good question. Okay, formally, what is happening is a protocol is defined by a length T and an alphabet sigma. This is fixed for the protocol. The adversary can only corrupt some fraction of T, many messages. And in any message, you can only send one symbol from sigma.
One, sorry?
And so every message is exactly one symbol from the alphabet. And you can corrupt a constant fraction of the messages.
So when you say constant fraction, it means that.
It means a constant fraction of t. T is the total length of the protocol, which is known.
But the length may be different for different runs of the protocol, right?
So we assume that t is the worst case. We assume that for all inputs, okay. The length is just t.
Okay, gotcha. Very good. Thank you.
Yeah. Okay, good question. So I will, like I said, I will ignore many details that are there in interactive settings. I will just focus on the simple message exchange task where Alice has an input X. Let's say this is n bits, and Bob has another input Y. Let's say this is also n bits. And they want to know each other's inputs. So Alice wants to know Y and Bob wants to know X. This task is actually completely general if you think about it, because regardless of what function you want to compute, it can be done by just exchanging the inputs. If you want to compute some function f of x and y, then here's one thing you can do is you can always just send x and y first and then privately compute the function. And this does not affect the error resilience, but it does affect the communication. Maybe the function f that you were trying to compute can be computed without sending the entire input, and it actually needs like very low communication to do that. But here I'm asking you to send the entire input. So it may be expensive in terms of the communication, but in terms of error resilience, this is not that much of a loss. I can focus on this, and I will still get error resilience results for all functions. So yeah, that's what I'm going to do. I'm going to throw communication out of the picture, and I'm only going to focus on error resilience. And it does not mean that my results will not extend to things that have low communication. Most of them do. Some of them do with a slightly worse parameters, and the techniques definitely do extend. It's not much of a change in terms of the main idea. So I think it's worthwhile for this talk to just focus on this one-way message exchange protocol. And one thing about this message exchange is that it's just two copies of the one-way message transfer. I had earlier shown a setting where Alice had a message M that she wants to send to Bob. Now, this Alice and Bob message exchange setting is just two copies of that. Alice wants to send X to Bob, and Bob wants to send Y to Alice. And what this gives us is that you can always run the naive protocol for message exchange in both the directions and get something for this general task. And that is what I will call the naive, that is what I'll call the naive protocol for message exchange. It will have a certain error resilience. And the point of this talk is to show that in two different settings, one setting where the alphabet is large but still a constant size, and in the other setting where the alphabet is binary, is to show how you can improve upon this naive protocol. It turns out that this naive protocol is actually pretty good in terms of error resilience, and it's hard to improve it. So we will have the same picture for both of them. We will have a naive protocol. I will show a barrier that exists for this naive protocol, and then I'll show how to beat that barrier and get a higher error resilience. So let's start with a large and constant size alphabet. So let's say alphabet size is some like 1 million symbols that you can send. And let us consider the message exchange task. Let us consider the naive protocol. I claim that the naive protocol for message exchange has an error resilience of 1/4. And the reason that is true is because if the total fraction of errors is less than 1/4, then the fraction of errors in any direction is less than 1/2. And there are error correcting codes that are resilient to a 1/2 fraction of errors. So you can just use the best possible error correcting codes in both directions. And this will give you a protocol for message exchange with error resilience 1/4. It may also seem that this is optimal, and this may be an attempt at a proof. Here is why 1/4 may be the best possible error resilience you can get. Suppose you have some protocol that is error resilient to a fraction that claims to be error resilient to a fraction larger than 1/4. The protocol has one party, let's say Alice, that speaks in less than half the rounds. So Alice speaks, if the protocol has length t, then Alice speaks in less than t/2 rounds. The budget of the adversary is at least t/4. So one thing that the adversary can do is it can corrupt the first half of Alice's messages to not resemble her true input x, but to resemble a fake input x prime. And he will let the other half of Alice's messages be the same. So the first half of Alice's messages will resemble the fake input x prime, and the other half will resemble her true input x. And now Bob receives half messages that say that Alice's input is X prime and half messages that say that Alice's input is X, and he cannot tell which one is the right answer. So this is an attempt at a proof, but this attempt assumes that one party, the adversary knows in advance which party is speaking in less than half the rounds. And this is indeed needed because the adversary needs to know even before the protocol starts. This attack only corrupts one of the parties. So he wants to know which of the parties he would like to bully throughout the protocol. And this is true for a lot of protocols, and it is true for all protocols that are non-adaptive. So formally, a non-adaptive protocol is one where for all rounds I in the protocol, you know in advance which party is speaking in round I. And because you know this for all rounds I, you can compute which party speaks in less than half the rounds, and you can run this attack. So for non-adaptive protocols, this does work, and you cannot get error resilience more than 1/4. But for adaptive protocols, this does not work. And the reason this does not work is because in an adaptive protocol, the order in which the parties speak can change during the protocol. So if you start to bully Alice at the beginning of the protocol, then the parties can detect this and they can give Alice more rounds to speak. And then you won't be able to corrupt half of Alice's messages because now she's speaking in more than half the rounds. And if you start to bully Bob at the beginning, then the parties will again detect this and they will now adapt the other direction and give Bob more rounds to speak. So now Bob will speak more than half the time, and again, this attack will not work. So not only does this attack not work for adaptive protocols, there is a better protocol that has a higher error resilience. But let us first take one slide and just fix what do I mean by an adaptive protocol. So here is the adaptive model. This was defined in GHS 14. And the most important feature of the adaptive model is that the order of speaking is dynamic. This means that there are T rounds. For each round I in the protocol, Alice and Bob take their input. They take everything they received so far. They take all the knowledge they have, and they decide whether they want to speak or listen in this round. Now, ideally, we want these decisions to be anti-synchronized. If Alice is speaking, then Bob should be listening. And if Bob is speaking, then Alice should be listening. And when this happens, then this channel behaves like a normal non-adaptive channel. The adversary can either spend one corruption and corrupt this message, or he cannot spend a corruption and then the message will be received directly. But because this decision of speaking or not speaking is made online, it is not guaranteed that they are anti-synchronized. So it may be possible that both the parties decide to speak in some rounds. And I will call these rounds collisions. And it may also be possible that both parties decide to listen in some round, and I'll call these rounds silences. So in the adaptive model, both collisions and silences are possible. They are a phenomena that is particular to the adaptive model. It does not happen in the non-adaptive case. And we will assume in this case that in both of these cases that the adversary gets to corrupt the channel for free. So in a round where you have a collision or silence, where 2 or 0 parties are speaking, the adversary can decide what symbols the parties get without spending his budget. And he can even decide on different symbols for both the parties, and he can use all the information he has. So it's like the strongest possible adversary. And we want to be resilient to more than a quarter errors for this strong adversary.
So, Raghuvan, just a quick question. Your models, you always assume kind of a synchronous model where there's kind of rounds and we know what round we're on. Is that right?
Yeah, that is true. Yeah, it is synchronous. So this is the adaptive channel. And now let's talk about how adaptivity gives you a higher error resilience. One thing before that, though, I started this section saying that the channel has a large and a constant size alphabet, but I will not, the protocol I will describe in the description, I will assume that the alphabet is large enough so that they can send the entire input in one round. So this is like an alphabet that depends on the input size. This is not like, this is only done for the sake of this talk. The actual protocol works with a small alphabet, a constant size alphabet, but I will not go into those details. I will just assume that here the input is, the alphabet is large enough that can contain the input and you can send it in one round. So you want error resilience 2/7. This is higher than 1/4 because 2/7 is 2/8 and 2/8 is 1. 2/7 is higher than 2/8 and 2/8 is 1/4. So we will have a protocol that has 7 n rounds. And because we are shooting for an error resilience of 2/7, that means that the fraction of the number of errors is less than 2/7 of 7n, which is 2n. These rounds will be divided into 3 stages of length 3n, 3n, and n. And the first 2 stages will be non-adaptive. And we know even before the protocol starts that Alice is speaking in the first 3n rounds. And she's sending her input x in each round. So that's why we assume that the alphabet can contain the input, because in every round she's just sending this input x. And in the next 3 rounds, Bob is speaking, and he's going to send his input y in every round. So the first claim is, in these 6n rounds, if a party receives 2n copies of some message, then the party can be sure that this is indeed the correct input of the other party. So if Bob receives 2n messages of some string here, then he can be sure that Alice's true input is actually that string. And the reason this holds is because the number of errors is less than 2n. And by pigeonhole principle, if you receive 2n copies of some message and the number of errors is less than 2n, there exists one of the copies that is not corrupted. And because that copy was not corrupted, that was indeed the true input of the other guy. So this is why this claim holds. And using this claim, we can also show that one of the parties is already sure after stage 2. So this is significant because the protocol hasn't ended yet. The protocol will go on for another n rounds, and I haven't even described what happens in these n rounds. But even before these n rounds, there exists one party. We don't know which one, but one party already knows what to output. So let's see why this is true. This is, again, due to the fact that the number of errors is less than 2n. This means that in one of the 2 directions, in either Alice to Bob or Bob to Alice, the number of errors was less than n. And because there are 3n messages, these numbers were chosen to make this happen. Because there are 3n messages and the number of errors is less than n, then there are 2n copies of the correct message for one of the 2 parties. And by the previous claim, if you have 2n copies of the same message, then you are sure. So one of the 2 parties is already sure after 6n rounds. Okay, so now half our job is done. One of the 2 parties is sure, and we have n more rounds to make the other party sure. So these n rounds will be adaptive. And what will happen here is that a party will only speak in these n rounds if they were sure after the first 2 stages. So if they are sure after this blue mark, then they will speak in the n rounds. Otherwise, they will listen in the n rounds. So the easy case is when both the parties are sure. In this case, both the parties will be speaking. There will be a collision, but it doesn't really matter because they're already sure. There's no way a sure party can be unsure of something. So that's the easy case. The other case by this claim is when one of the parties is sure, but the other party is not sure. And in this case, let's say Alice is sure and Bob is not sure. Alice will be speaking in the last n rounds. Bob will be listening in the last n rounds. And at the end of the protocol, Bob would have heard Alice for a total of 4 n rounds. 3 n rounds at the beginning here, and then the last n adaptive rounds. Now, because Bob heard Alice for a total of 4 n rounds and the number of errors was less than 2n, Bob knows that the majority message he received is correct. And therefore, after 7 n rounds, he can just decode by majority and be sure of Alice's input. So this is the complete protocol. You have rounds 3 and 3 and n, non-adaptive, non-adaptive, adaptive. Alice sends to Bob her input. Bob sends to Alice. Yes, is there a question?
Actually, I have a question. What is n?
So n here is a constant that depends on the exact error resilience you want. The way this will work is you will give me an epsilon, and I'll give you a protocol with error resilience 2/7 minus epsilon.
Okay.
And this n
goes with 1 over
yeah,
epsilon.
yeah, this will be like 1 over epsilon. Yeah, it's some constant here. Maybe n is misleading. But yeah, this is the entire protocol. You have adaptive rounds and non-adaptive rounds and adaptive rounds, and this gives you error resilience of 2/7. So here is how the scenery looks like. You have 1/4, which was non-adaptive. You knew this was the best possible. And then I gave you a protocol that was 2/7, but it was adaptive. And the question to ask is this the best possible for adaptive protocols? Is this the highest error resilience you can hope for? And it turns out that there is a barrier at this value, 2/7. And you know that many classes of protocols cannot beat this error resilience benchmark. And these actually include many natural classes. For example, you may assume that a protocol needs to be alternating, where Alice speaks in all rounds and Bob needs to speak in even rounds. If you have a protocol that is alternating, then you can formally show that you cannot get error resilience 2/7. So this protocol was not alternating, but it can be made alternating. That's not a big deal. But yeah, for alternating protocols, you can not get more than 2/7. Similarly, you would expect that message exchange is a symmetric task. So maybe the protocol should be symmetric between the two parties. You can also show that for symmetric protocols, you cannot beat better than 2/7. And there are many other things. For non-interactive protocols, you cannot beat 2/7. There are many such barrier results. But what we show is that using one new idea, which is the idea of feedback, you can get an error resilience that is larger than 2/7. And this is what I'll describe next. I will describe how one idea helps us break this barrier, and we're actually the first one to do that. So let's see. We again have this protocol. And the first thing to note here is that in this protocol, Alice is really trying her best. All she knows when she speaks in the first 3 rounds is her input X. And she's just sending this input X in every round. So she's really trying hard, and she's sending Bob everything she knows. And that's all she can do. But Bob is not doing his best. When Bob speaks in this set of 3 rounds, then he not only knows his input Y, but he also knows what he received from Alice in the first 3 rounds. And he does not send this extra information. He only sends this input Y. And the main idea, what I mean when I say feedback, is if Bob sends some statistics about this part of the protocol, if Bob can tell Alice that, oh, I saw these many corruptions in the first stage, then maybe Alice knows that there were some corruptions from Alice to Bob, and she can just be sure faster. And if she can be sure faster, then the error resilience will be higher. So this is what we want to do. We want to make sure that Bob sends some statistics about the first phase. In the second phase, this will be the feedback. And if there were many errors from Alice to Bob in the first phase, then this feedback will mean that there can only be few errors from Bob to Alice, and Alice will be sure faster. So this is an improvement. And if there were few errors from Alice to Bob in the first phase, then this is also an improvement, because Bob is just sure faster, because like few errors is the easy case for Bob. So it is a challenge to precisely define what should be the feedback and how should it be sent. Another challenge is to make sure that the adversary does not corrupt the feedback itself, because it's also sent over the same channel and it can be corrupted. These tasks are there. You need it to be communication efficient even. And all of these things require care, but I will not go into those details. I will assume only one bit of magical feedback. So Bob doesn't have to send anything, but there will be an oracle that will, after the first 2 stages, tell Alice whether Bob is sure or not. So it's just one bit, whether Bob is sure or not, and it is revealed to Alice after the first 6 rounds have taken place. And what I want to show is that with this one bit of magical feedback, you can get a higher error resilience. So the way the proof will go is I will keep the number of errors the same. The number of errors will be 2n, like it is right now, but the protocol will now be shorter. So I will now have protocol with 20n/3 rounds. This is less than 7n. It is indeed less than 7n. And the breakup is different. It's 8n/3, 8n/3, and 4n/3. These numbers don't really matter. They just need to make the calculations work. But because the protocol is shorter and it has the same number of errors, the fraction of errors is larger. And therefore, this gives you a higher error resilience. So let's see why this is. So it is still true that because there are 2n errors, it is still true that if you receive a message 2n times, then you will be sure that the message is correct. What I will show is the other claim. What I'll show is that even though these phases are now shorter, they were 3n initially, now they are shorter than 3n. Even though these are now shorter, one of the parties is still sure after the second phase. And the rest of the calculation will go exactly as before. So let's see why this is true. We want to show that one of the parties is sure after the second phase, after 16n/3 rounds. And here is how the proof goes. If Bob is sure, then there's nothing to be done. If Bob is sure after 16 and over 3 rounds, we are done. If Bob is not sure, then we have this assumption of magical feedback. And this means that after these 16 and over 3 rounds, Alice knows that Bob is not sure. So she can conclude that Bob did not receive 2n copies of any message. And therefore, she can also conclude that at least 2n over 3, which is 8n over 3 minus 2n, copies of her messages were corrupted. Because if not, then Bob would have received 2n copies and he will be sure. Okay, now the budget of the adversary is less than 2n, and this was at least 2n over 3 of that budget was spent from Alice to Bob, which means that Alice knows that less than 4n over 3 messages from Bob to Alice were corrupted. This number is just 2n minus 2n over 3. And now, because the total number of messages that she received from Bob is 8n over 3 and less than 4n over 3 messages were corrupted, she can decode by majority. She knows that the majority message is correct, and she can, because she knows all of this, she can decode by majority and she can be sure of Bob's input. So I proved that if Bob is not sure, then Alice is sure. So one of the parties is always sure after the second phase. And by a similar analysis as before, you can show that both the parties are sure after the third phase and the protocol works. So overall, what I gave you was, I gave you a protocol that has error resilience higher than 2 over 7. The exact number is 2n divided by this number, which turns out to be 3 over 10. This worked under the assumption of this magical feedback. It was adaptive. But again, you can ask, can you do even better than that? It turns out you can. In fact, these ideas themselves are sufficient to get something even higher. This is just a simplistic view of the protocol. We now know even the exact constant. We have a matching upper and lower bound. It turns out to be 5 over 16. But these ideas do not get you all the way to 5 over 16. They only get you a part of the way, and then you need another idea to get you to the exact optimal. But that's another paper. For now, let us go back to error resilience and let's go back to feedback. So all of what I said was about a protocol that can use a large alphabet that is still constant sized. And now the next part of the talk is the exact same question, but in the case of a binary alphabet. So here you again have two messages. Alice wants to send a message to Bob and Bob wants to send a message to Alice. But this time the alphabet is binary. They can only send bits 0 and 1. In particular, they cannot send the entire input in one round. So this is the next part of the talk, but this is a good place for questions about this part of the talk, if there are any.
Can I ask a question?
Yeah.
So this assumption that Alice magically knows,
Yeah.
do you realize this assumption or do you assume it?
Oh, no, we actually realize it. We design a feedback. That's a good question. Yeah. Our protocol is not assuming magic. We are still on earthly world. We design a feedback mechanism. We made sure it's powerful enough so that even if some of it is corrupted, because the adversary can also corrupt the feedback, even if some of it's corrupted, Alice still gets enough information to make the protocol be more error resilient.
Okay, so in other words, you don't assume feedback. You realize feedback.
Yeah, we create feedback in a channel that has no feedback.
Okay, thanks.
Yeah. In fact, if you give me feedback for free, then I can give you a much higher error resilience using a much simpler protocol. And this is known. I think you can get like, even the right answer is known. The right answer happens to be 1/3. And for the feedback channel, it is known to be tight. So that is an easier case of this work. Here, we're trying to create feedback in a channel that does not promise it. Here, it's an artificial version of the feedback that we want. Okay, so let's move on to the next part of this talk. The question is the same. There is this message exchange task that we want to do under a under a larger and larger fraction of errors. And there is a naive protocol that just uses error correcting codes in both directions. So it turns out that once you go to the binary setting where Alice and Bob can only exchange bits, then the maximum error resilience you have from error correcting codes is only 1/4. For example, you may consider the Hadamard code That only gives you the error resilience 1/4, and it is the best possible. Even the long code, I think, is 1/4, and that is also the best possible. And because in one direction you have error resilience at most a quarter, what this means is that the error resilience of this message exchange task will be 1/8, because you want to do 2 copies of these error correcting codes, and you want the error resilience, you want the errors in both the copies to be less than 1/4, which means the total fraction will be half smaller, so it will be 1/8. This is the naive protocol for binary. It has an error resilience of 1/8. And in fact, nothing better is known. This is known since a decade. It's actually trivial to do it for message exchange. It's also known for more general functions, but for message exchange, it's particularly simple. But we don't know anything better. And there is a reason we don't know anything better. There is a barrier at 1/8. And the barrier comes from 3 properties of the message exchange task. So when we talk about message exchange in the binary setting, the first thing we want is a binary alphabet. Our protocol can only send bits. And usually what this means is that you lose a factor of half in the error resilience, because even for error correcting codes, the best possible error resilience you can get using a binary alphabet is a factor of half smaller than the best possible error resilience you can get using a large alphabet. And this is prevalent even in tree codes. It's prevalent throughout the interactive coding or the coding theory scenario. And it's a well understood fact that binary costs you a factor of half. So this is the first half in 1/8. The second half in 1/8 comes from the fact that we require Alice and Bob to output the message exactly. This is the unique decoding requirement. Alice needs to output Bob's message exactly, and Bob needs to output Alice's message exactly. And the reason this costs a factor of half is roughly because if you have 2 code words that are some distance d apart, and you want unique decoding, then you can only tolerate d/2 errors, because after d/2 errors, you're somewhere in the middle and you don't know which one is the right one. So when you want the correct answer uniquely, you need to lose a factor of half. This is as opposed to list decoding, where you want to output a small list of values such that one of them is correct. And there you don't lose this factor of 1/2. So binary alphabet requires a factor of 1/2. Unique decoding requires a factor of 1/2. A third property of the message exchange problem is that it's a 2-way task. Both Alice and Bob have inputs that they want to send to each other. And this again tends to cost a factor of 1/2, because you want to run the one-way protocol in 2 directions. And you want the total error to be small, where you want the total error fraction to be small, but the relevant error fraction is just the error fraction in one of the 2 directions. The adversary can just focus all the errors in only one direction, and that costs you another factor of half. So these are the 3 factors of half that are present in binary message exchange. This is why you get a factor of 1/8. But this in itself does not mean a barrier. You have 3 properties, sure, that have a factor of half each. Maybe they're not independent. Maybe you can do something that combines 2 of these in a clever way. And maybe an improvement is possible. It turns out that it is not possible. It turns out that it is known that, okay, I said this, each requirement costs a factor of half. It is known that even if you combine 2 of these requirements, you cannot get an improvement. For example, if you combine binary alphabet and unique decoding without the 2-way task, so it's the one-way setting with the binary alphabet and unique decoding, so it's the error correcting code setting, you know that you cannot do better than the product of half and half, which is 1/4. So these requirements behave independently, at least these 2, for matters of error resilience. And it's not just these 2, even these 2. If you want 2-way task, which is message exchange, and you want unique decoding, but you don't want a binary alphabet, so you are okay with the large alphabet, then, like I said, you cannot do better than 1/4. Oh, I should mention, everything here is non-adaptive. We are not doing anything adaptive here. So for non-adaptive protocols, I said that there's a lower bound that's matching. It's 1/4. And you can't do better than the product of half and half. So that's this case. You also have the third combination, which is binary alphabet and 2-way task, but with list decoding this time. So you don't have to output the answer exactly, but you have to output a small list such that one of them is correct. And even for this combination, it is known that you cannot do better than the product of half and half, which is 1/4.
Sorry, yeah. So all these lower bounds are for the non-adaptive setting?
So let's see. So in error correcting codes, there is no adaptivity because it's a one-way task.
Yeah.
Here, this is for non-adaptive settings, and we know it's not true for the adaptive settings, like I just showed. And what breaks is that it's no longer a two-way task. You don't have to run two independent copies because they are adaptive.
Mhm.
This one, I do not remember. So this BE17 paper did not show the lower bound. This was an observation that we observed from their work. I'm not really sure if this was non-adaptive or not.
Okay.
But it probably was. I don't think we mentioned adaptivity anywhere in the work. So this is probably also for non-adaptive protocols.
Got it. Okay, thank you.
But
Sorry,
the point,
one more question. I probably missed this. So I understand that each of these 1/4 is tight, which is really cool. Is the 1/8 really tight? Because supposedly I could have imagined a case where the third one that you add is for 3 for any of these.
So you're stealing my thunder. So okay,
let me answer
that.
Sorry.
Let me answer that. Okay, these requirements cost a factor of half. They are independent pairwise. You can take any two and you can get 1/4. But what we show in this paper is that they are not mutually independent. If you combine all 3 of the requirements together, then you can get an error resilience of more than 1/8. So
awesome. Thank you. Sorry for.
It's okay. So yeah, this slide covers the entire picture. You have this 10-year-old problem where you have a naive protocol that gets 1/8. There was a well understood barrier, which is you have 3 requirements. They are pairwise independent. You don't know how to combine them. But what we show in this work is you can actually combine all 3 together and you can get an improvement. In fact, we don't try to even optimize the resilience here. We just focus on getting something that is higher than 1/8. And even that is, I think it's a very strong result because I don't think there are many phenomena like this where you have pairwise independence, but you don't have mutual independence. Okay, so let's see, the next protocol is this paper. We want to get a protocol that has error resilience more than 1/8. We are in the non-adaptive binary setting. There is no adaptivity. The exact error resilience that we will go for is 5/39. It's more than 5/40, which is 1/8. Like I said, we didn't optimize it. It can probably be improved. We don't have a matching lower bound. But let's go to the protocol. We have 39 n rounds. The error resilience that we want is 5/39. So the number of errors is less than 5n. And we divide these rounds into 3 stages. The exact lengths are 16n, 20n, and 3n. They add up to 39. And these numbers are chosen because you have some parameters for error correcting codes that you want to satisfy. So these are basically chosen to make the analysis work out. And I will try to explain why they are what they are. But important thing to note here is because we have a binary alphabet, we cannot, like before, afford to send the entire input in one round. The reason you did not have any error correcting codes in the previous protocol that I described is because I just assumed that you can encode the entire input in one message and send it across. And then you don't need any error correction because either the entire message is corrupted or none of it is corrupted. So that's not true here. We actually need some error correction, and that's the whole point of this protocol. We need binary codes that have high error resilience. So this part of the protocol has to be complicated. I need to talk about the parameters you have. But let's see what they are. So there are 3 stages. The first stage has 16 n rounds. And in this stage, Alice sends her input x. Oh, sorry, one more thing. This n is now the length of the input times a constant factor. And this just means that the communication overhead is only a constant factor because you at least have to send your input. Okay, so in the first 16 n rounds, Alice takes her input x and she encodes x using a list decodable code with a list of size 3. So it's a very small list. You want a list of size less than equal to 3. And Alice just takes such a code and she can send her input using this code to Bob. It turns out that the best possible parameter you have for such codes is that you can promise that the error resilience of such codes is 5/16. And this is tight when it comes to list decodable codes for lists of size 3. And because the error resilience is 5/16 and you have 16 n rounds and 5 n errors, this part of the protocol will work directly. At the end of this protocol, Bob will be able to successfully list decode. The fraction is less than 5/16. And he will get a list L of size at most 3 that has Alice's input in it. He does not know which one of the three elements in the list is Alice's input, but one of them is. In the second part, Bob takes his input Y, he takes the list L that he computed in the first round, and he encodes this pair Y comma L using a standard unique decodable error correcting code. And Alice just unique decodes. So once you have a unique decodable error correcting code, the maximum error resilience you can hope for is 1/4. And again, the length is 20 and the errors is 5n. So the fraction of errors is less than 1/4. And therefore, I can promise you that this part will also work correctly. And at the end of stage 2, Alice will know Bob's input Y, and he will also know she will also know the list L that Bob computed in phase 1. So this is half the job done. Alice already knows Bob's input Y, but Bob still does not know the input X. Bob has 3 candidates for it. He needs to know which one. Luckily for us, Alice knows exactly which of the 3 candidates Bob is considering. Alice knows the list L. So in the third part of the protocol, all Alice does is she takes a small error correcting code and she only sends the index P in 1, 2, 3. This only has 3 possible values of X in L. And this is where the magic happens. This is a unique decodable code because now Bob needs to output the answer exactly. But it has error resilience more than 1/4. And the reason we're able to get error resilience more than 1/4 is because we only need to encode 3 messages. Alice will ever only send 3 messages. I'm sorry, can you hear the beep from my computer? I can turn that off.
I didn't hear anything.
Okay, then it's just me.
But since you asked a question, what do you mean by small error correcting code? You just mean that you can encode one of 3 elements? Is that what you mean?
So that's what I'll just answer that in 1 minute. Okay. But this smallness of the error correcting code gives us a higher error resilience. And what do I mean by smallness? I mean that the error correcting code has only 4 code words. Usually when you want error correcting codes, you're worried about the asymptotics. You want to encode many messages, let's say to the n messages, and you want code words for each one of them. Here I'm not in the asymptotic regime. Here I'm in the small n regime, and I only have an error correcting code with 4 code words. And I claim that there exists an error correcting code with 4 code words that has error resilience 1/3. Here is such a code. You have these 4 code words. One of them is all zeros. The second one is ones till 2/3 of the way, then zeros, and then the other 2 are as shown. And it can be observed that the distance between any pair here is less than 2/3. For example, between C0 and C1, they differ in the first 2/3 coordinates, so the distance is 2/3. C0 and C3 differ in the first 1/3 and the last 1/3, and that's also 2/3. C2 and C3, you can do this for any pair. C2 and C3 differ in the first 2/3. And basically every pair of code words here differ in 2/3 fraction of the coordinates. And this means that if you want to unique decode, you lose a factor of half and you get error resilience 1/3. So because you had a small code here, you were able to get a better error resilience. And this error resilience actually gave you a better error resilience overall, and you were able to beat 1/8. So I can analyze this protocol. I can show that it works, but I won't do that. What I will do is I will show how we get around the 3 barriers that I talked about. We had 3 barriers, which was the binary alphabet have a cost of 1/2. We had unique decoding that has a cost of 1/2, and two-way task has a cost of 1/2. And let's see how we break each one of them together. So the first barrier is that you cannot do unique decoding without losing a factor of 1/2. And we get around that by considering list decodable error correcting codes. In this phase, we are able to get a resilience higher than 1/4 just because Bob is list decoding to a list L. It does not matter that the list is size so small, it's only 3, but it's more than 1, and that is enough to give us an improvement. The next barrier is the fact that in a two-way task, you generally lose a factor of half because the adversary only needs to fail one of the 2 directions. And the reason that doesn't happen here is because these 2 tasks are not independent. In order for Bob to know Alice's input, Alice needs to know L because she wants to compute the index P. And this interaction makes it non-trivial. You need to interact, and this is the feedback that Bob is sending here. And this gets around the barrier of two-way task. The third barrier was of the binary alphabet. I said that the binary alphabets have an error resilience that is a factor of 1/2 smaller than the case for the large alphabet. And we overcome this barrier by considering powerful binary codes that have only a small number of code words. And it is interesting that it is actually not the asymptotics that matter for this protocol. Even though asymptotics is what we care about in the classical setting, for this interactive setting, it can actually be these low size codes that can make an improvement in the error resilience setting. Is there a question? I hear some buzz. Okay, no. So this is how we get around each of these three barriers, and you can see these three things need to really work together for this protocol to work. Bob needs to list decode so that he can send something to Alice. Alice needs to hear something from Bob so that she can compute an index P. And this list needs to be sized very small, some constant, so that she can use a powerful binary code and she does not run into the asymptotic lower bound that is at 1/4. So that is it. That's how you beat 1/8 for binary. And that's all I have for this talk, I think. Yeah, that's all I have for this talk. So yeah, I'm happy to take questions now.
Okay, thank you very much. This was great. So
yeah, I'm stopping the share and I'm turning my camera on. Hello.
There you go. So
there was an extra slide after the thanks. We want to see it.
Oh, that was just references. You want to see the references? Like I used the BibTeX. Some of the BibTeX slides were after that.
So any questions? Okay, while people may think about whether they have a question, I'll ask one. So you showed in the last part, right before the end, how you can get a small, what you call the small aircraft encode, where the set was of size 4.
Yeah.
But actually, your list was of size 3.
Yeah.
So if you can make the list of size 4. I don't know how, like, what's the maximum number of code words you can get for your small, but don't you don't, I'm guessing you don't benefit from getting a list of size 4?
Yeah, that is the reason we don't benefit. This was very depressing. We came up with this tool idea and we thought we only need lists of size 3 or maybe even 2, like we had these things. But it turns out that for when it comes to list decoding, the numbers come in pairs, at least for binary. I don't know if this is the case for ternary or quaternary, but for binary, the error resilience that you can get for list decoding with size 1 is the same as that you can get with size 2. And again, for 3 and 4 is the same, and 5, 6 is the same. So we had to go to, it doesn't matter if you're 3 or 4. And another reason why this is interesting is because this was for message exchange. If you go to the general interactive function setting, then this does not really work as is, because in the interactive setting, Bob does not have like 20 enrons in the middle of the protocol. He needs to interact throughout. He cannot wait all the way till he gets the list. And because he cannot wait all the way till he gets the list, there's a chance that Bob's list may be wrong. And using the 4th code word, we can convey this information. Like if Bob is not sure about his list, then he can use the 4th code word. And it's lucky and unlucky in the same at the same time. It's lucky because in the interactive setting, we don't lose anything. We get the exact number that we had in the message exchange setting. It's unlucky because we don't get a higher number in the message exchange setting.
Yeah. Interesting. Okay, great. Great. So anybody have any other questions?
Is it okay to ask a general question?
Yeah.
So I guess I was trying to understand. So sorry, I'm not in the area. I don't know. Like I'm trying to understand generically. So you have all of these new protocols that achieve better, rates of transmission, like with fewer maybe messages. So how do you go? What is the path from finding this better messaging scheme to actually having it be part of what people use in their daily lives in cryptographic exchanges or something? You know, how do you go from the thing that you found in your paper to making that part of something as widespread as RSA or something? And are there blocks, roadblocks in the way that are theoretical or practical? That's what
So that is a good question. Another similar question that people may have is that why do we even care? Throughout computer science, we ignore the constants. And here I'm talking about an improvement from 1/8 to 5/39, which is just like a less than a 1/1000 improvement, I think, or something like that. And these are great questions. The reason these words still have significance is because of the barriers. For example, usually, like I said, when you go from a large alphabet to binary, you lose a factor of 1/2. And this is present everywhere. There are many cases where you want codes for binary alphabet and you only have codes for a large alphabet and you just lose a factor of 1/2 and you get something. But what this word is showing is that this is not necessary. You can do something. You can use the small error correcting codes, or you can use whatever, and you can get an improvement of the factor of 1/2. The other word similarly is showing that adaptivity is not the only thing you need. You actually need to send feedback. You cannot afford to be symmetric and just run the same protocol in two directions. You need one party to be sending feedback and the other party to be receiving feedback to get the optimal thing. So I think these high-level messages are what will design those, are what will inspire those practical applications. And maybe they don't get all the way, but they will still get some improvement over whatever they are currently.
So you're saying that the main highlight of the contribution here is like the tightness of the lower bound and the upper bound, or something like that?
It's actually more just the idea of using feedback and the idea of using small codes and the idea of combining them, like just these things that you can do something. We did not know what to do to beat those barriers, and I'm just giving you this one idea of feedback that gets around this. You need to adapt it in different settings. One setting you just one setting you use small codes, other setting you need some other things, but this one idea of feedback can give you an improvement in the resilience in a large array of settings.
Thanks very much.
Any other questions? So Vasilis, by the way, just up from my perspective on the same thing, in general, communicating while being resilient to error is a fundamental problem that I have no idea if today this is used or what's being done, but it is you want to ensure that when you communicate, you're able to understand each other despite errors. So, and understanding what's the best error you can do for is important.
That's what, these are so fundamental processes, and I'm asking, why isn't like every time that you find something slightly better, it doesn't go into something that people use every day in such cryptographic communications,
actually it's not even cryptographic, it's in general communication, right? So that's a good question. I actually don't know what's being used today. I don't know if people, when they I think of course when you just send one-way communication, they do use error correcting code. That's used all the time. Again, I'm not sure which one exactly what they use, but in interactive, when it's a two-way communication, I'm actually not sure if it's already, it's a relatively new topic. There was the classic results, but the idea of this research of kind of improving error results in interactive communication, it's from the 90s, so I don't know if that's by now in our standards new or not, but I don't know if it's actually being used.
I see. So people don't know what the agencies are using, for example, like the government agencies or something when they want to do.
I have no idea. Yeah.
Okay.
Yep.
That's a good question. Okay, so let's think, unless someone more questions, I'm guessing. Okay, thank you, Agvan. It was great.